Okay, hi everyone. Let me put a timer, otherwise I'll go over time for sure. So my name is Alekos. I'm one of the co-founders of this company called 22, and we make Bitcoin hardware devices. And the presentation today is more about my journey building Portal, which is our first and only device right now, which is an hardware wallet. It's a mobile optimized hardware wallet, on-chain hardware wallet. And I'm going to start by saying at 22 we love open source. So obviously our devices are fully open source. So the hardware is open source, the software is open source. But we also want to be very open about the process of building hardware, of coming up with new ideas. And again, this is why I'm doing this presentation. So I just want to open source kind of the story of Portal and how we got to it. Yeah, I hope you will enjoy it. So, well, as with any project, you start with the vision. So the vision for Portal was we want to make an hardware wallet that's specifically optimized for mobile, because there are a bunch of solutions out there in the market today, but we feel like none of them really works well with mobile. So some of them cannot work straight up with mobile. Some of them do work with mobile, but then you have like Bluetooth, which is kind of annoying to use, or you have cables and stuff. So we wanted to make something specific for mobile that works well with mobile. And when you go the mobile route, you also go you kind of attract average users. So obviously, people in this room, probably super techies kind of people, they don't want to use mobile for the wallets, and I guess it makes sense. But for most people, a smartphone is the only thing they have. It's the only like digital device they have, they know how to use. So for those average people, you need to make easy to use products, kind of intuitive products that are not too technical, too complicated. And finally, obviously, we wanted to make it open source because, again, we want to be as transparent as possible. So we want to let everybody see the code, audit the code, see what's going on in their devices. So this was kind of the original vision. And these points kind of all converge a little bit on NFC, or at least the first 2 points kind of converge on NFC, mainly because, first of all, it's much easier to use than Bluetooth, for example. You don't need any pairing or anything like that. It just kind of connects immediately. It's immediately available, and it works everywhere. So it works both on iOS and Android. While, for example, if you use cables like USB cables, you can plug in a USB hardware wallet in an Android device, but you cannot do it on iOS due to Apple restrictions and stuff. So NFC is kind of universal, works well. It's pretty quick. You can transfer information quickly, probably much more quickly than using QR codes, which I find very annoying in my opinion. And the cool thing about NFC is that it's not just bidirectional communication, it also transfers a small amount of power. So from an active reader, which is your smartphone, you transfer some power to the device. And this is super cool because we realize, well, maybe we can power the whole device just from this power. So we don't need any batteries, we don't need to recharge a battery or anything like that. We just power straight from the phone itself, so wireless charging kind of thing. But obviously it introduces limitations because the power is very limited. And the other thing, obviously you want to build another wallet, the other thing you need to consider is the security model. So for that, you start from who is our target audience, especially how can they screw up and how can we make them not screw up. So again, we're targeting average people. So we want to make something super easy, no menus, no things to navigate, otherwise people get lost and they make mistakes. So on the UI side, we try to build something like very kind of straightforward. Originally, the idea was to not have any protection. So I mean, we do have a display, so we show the user what's going on. That's very important because it's easy for somebody not technical to be convinced to download an app, like download this app to update your firmware, and then you tap it and you accidentally, unknowingly sign a transaction. So having the display is very important to avoid that. So when you tap it on the display, you can see what's going on. And initially the idea was no protection, so it's just a physical bearer tool. Because again, doing that I think suits well non-technical people. You bring the problem of securing Bitcoin to the physical world, and the idea is you just have to physically secure this thing, which maybe for us it's not so good, but for average people that are not really familiar with technology, that's probably easier to understand and easier to reason about. So the original idea was no protection at all, just a physical thing, whoever has this can use it. And then I was convinced by, I think it was Giacomo Zucco, he convinced me to add a mode. So now in the real device you can do both. You can have no protection, or you can have what we call the pair code, which is like a shared passphrase between your phone and the device. So then only your phone can unlock the device. And the memory on the device is effectively encrypted. So if somebody steals your device while it's encrypted with this pair code, they cannot do anything with it. So now we support both modes, and they have trade-offs, and different people may prefer one or the other. And we decided against the secure element for a bunch of reasons. One of them was limited power budget, because we are powering everything straight off the NFC. And the other thing was, well, the flash is encrypted anyway. So if you use this mode with encrypted flash, the flash is encrypted. So at cold, in a cold state, when the device is powered off, a secure element doesn't really add any extra safety, because again, the flash is just kind of encrypted. So even if you manage to extract it, which is still not so easy, that you can't do anything with it. And so from then, you start with prototyping. So that's probably pretty obvious. As with any project, you design the board. We use KiCad. It's like an open source tool, so it's very easy to access our files if you want to hack on them. You order boards from a manufacturer. Luckily nowadays there are manufacturers in China that produce like even 5 pieces, 10 pieces very cheaply, very quickly. You assemble the board. I usually would assemble them myself because it's cheaper than buy assembly service for low counts. So I assemble them myself with, place the parts, you put it in an oven and it solders. Then you test it and rinse and repeat, and you do a bunch of iterations. And for us, we got pretty lucky. So everything worked on the first try, which is what we called board revision 2A. But then so initially the idea was it's just a bare board. That's the product. Then we realized, well, maybe we need a case. We need some kind of protection, especially, like people maybe have wet ends or something. They touch the component, they can short them. So then we made revision 2B, which is slightly bigger, and then we moved the components to the back with the idea of we're going to add a case to the back to protect the components behind. Then we realized, well, maybe we need a case in the front as well to protect the display. So then we made revision 2C, which introduces notches to assemble a case in the front as well. And then finally 2D, which is when we realize using screws is easier than fine-tuning tolerances for snap fit parts. So we were like, screw it, we're going to use screws. And we did revision 2D. And this is like pictures of the whole process. So starting from revision 2A, which coincidentally was almost exactly a year ago. So obviously the project started earlier. Revision 2A was finalized on August 26th of last year. Then November 30th, January 25th, and April 20th, the last version. And you can see kind of the evolution. So there we had all the components in the front. At that point, I didn't bother 3D modeling the display. So obviously the display was there, but it's missing in the rendering. Then we did second revision, everything on the back. And you can see it actually here. So this is the back. You can see we moved all the components on the back. And then this remained pretty much the same. We just slightly moved the display to center it from 2B to C. And then we just changed the shape and we added notches and stuff. So this is like the whole flow, the whole set of iterations that we did. And so this is, again, obviously there's so many things to say about the hardware. I only have 20 minutes, so I have to cut it short. I also want to talk a little bit about the firmware. So a bunch of random facts. Again, I could talk for days about this. The firmware is fully written in Rust, in no STD Rust, so like a subset of Rust that can run on embedded hardware. It's based on Rust Bitcoin and BDK. We recently updated to BDK 1.0 beta 1, which is a big thing. If you know BDK, that was a big milestone. And a few, random facts about the firmware. One cool thing is that we can update it through NFC, but that forces us to halve the flash size because we have, instead of having one all flash memory, we divide it in half, and we have 2 banks. So we have one running bank, and the other one is the one we flash to. So if something goes wrong during the update process, you still have a valid running firmware, which is pretty standard to do. Like routers do that as well, but that halves the capacity of the flash, so that's not great. And then there's a bunch of other, I call them neat tricks we do in the firmware. Some of them, like the first one, is due to the constrained power. So everything is async Rust, and we put the core to sleep while we wait for something to happen. So it could be we're waiting for a message to come. When a message comes, we get an interrupt. So we can put the core to sleep. When the interrupt comes that the message is here, we can wake up and process it. Or we are waiting for, 20 milliseconds for something to I don't know, let's see if the user releases the button or something like that. I want to wait 20 milliseconds. I'm going to go to sleep, get an interrupt from the timer 20 milliseconds later, and wake up. And so with that, we can save a little bit of power. Another cool thing is we managed to preserve the state over short reboots. So we found some registers that maintain the content even for, I don't know, up to 500 millisecond kind of reboots. So you can remove the power for 500 milliseconds and the content remains there. And we use that because iOS has some limitations on timeouts and stuff. So sometimes on iOS you have very short reboots, like 50 millisecond reboots. And we managed to preserve the state, so from the user perspective, you don't really notice it, or maybe you see like a lag or something. But it's the old device rebooting and starting over from where it was before rebooting, all happening like seamlessly, which was fun to implement. And also for development, I forked QEMU, I don't know how to pronounce it. I implemented the peripherals we use, the STM32 peripherals that we use, and so then I can just take a binary that would run on a real device and run it on my laptop, so I can debug it, and it's just easier for development. Now, at this point, you have hardware, you have software, so that's it, right? You can sell it. Well, no, there's what I call everything else, which is probably the vast majority of where the vast majority of my time went. So all the things that are not hardware or software, everything else that goes around it. So one of them, for example, like literally goes around it is the plastic case. Again, we started with no case, and we were like, well, maybe we're going to have a case on the back. Then, well, we need something in the front as well. And then we needed to optimize the model for injection molding. This is actually when we contracted the company to help us on that process, because if you screw up the molds, they're like few $1,000s of molds. If you screw them up, then you have to make them over. So we're like, well, maybe it's worth paying a company to help us to not screw them up. Another thing, for example, is packaging. So how do you package this thing? What we settled on is we put the device in a tamper-evident serialized bag. So you have every device has a unique bag with a unique serial number, which is also flashed on the device. So when you power it on, you can like double check it. Then we put it in a box. So we custom made, we designed a custom box with padding inside. We put the envelope in the box to protect it, just during shipping and stuff. And then we had a problem, which was we need to print the serial number on the outside because of some things that are not ready yet. We're gonna announce soon, but we have some plans for that. It would be easier to implement, I guess, with some logistic plans. I guess they're easy to implement if we have the serial number on the outside. So we wanted to print the serial number on the outside. So we bought like a label printer, off the shelf label printer, to print those labels that are the one stuck on the side of the device. And then we also needed to somehow keep the box closed. And we tried those, like transparent stickers transparent round stickers that you find everywhere. We bought some of those, we tried them. Maybe we just got a bad brand or something. They didn't really stick or anything, they sucked. And so then we realized, well, we have a label printer, we can just print like a sticker that keeps the box closed. So that's like the design of the sticker that goes on the edge of the box to keep it closed pretty much during shipping. Then there's compliance, which is a big mess. I'm not gonna get into that, but when you want to sell electronics, you need to prove that they are safe to handle, safe to use. So yeah, it was a mess. Luckily, I wasn't the one dealing with this. My co-founder was. And we still don't ship to some countries, mostly not because the device is illegal there, but because we need a proper documentation, and it costs money and time to do it. So sorry if we don't ship to your country yet. Then in terms of production, we really wanted to control especially the most sensitive step, which is flashing the firmware on the device, because that's where like a malicious manufacturer could flash a malicious firmware. So what we do is we order kind of individual parts, or at least we order like a fully assembled board, we order the plastic cases, we order the boxes, and we assemble them ourselves, which is it's fine for the volumes we're doing now. At some point, probably we're going to have to either hire somebody or find a reputable manufacturer, but for now, it's fine. And the cool thing is I realized doing this project how many tools you need to do stuff. So, you want to build an hardware wallet, but you also need tools to build the hardware wallet. So in this case, specifically for the flashing, we developed, we 3D printed like a jig, like a thing where you place the board inside and just holds it in the right place so that you can flash it. And this is kind of a recurring thing. We develop tools everywhere to help us doing our job of producing and shipping and whatever those devices. In terms of logistics, initially the plan was we just stick the label on the box itself. Then we realized maybe it's not so good for privacy, like to know that so everybody in the transit like chain can see that you're buying an outdoor wallet. Maybe that's not great. So then now we wrap them in some other kind of anonymous package, or like a DHL, envelope, whatever. We developed again scripts and stuff to automate as much as possible the shipping process. So I have Python scripts. You take the orders from Shopify, download the CSV of the orders from Shopify, process it, produce another CSV that you can upload to DHL. And it was really fun to reverse engineer the format because obviously they don't document it well. Or to another shipping courier we use in Italy. Then this creates the shipping labels. This website I linked there is yet another example of a kind of tool I developed, which is unfortunately it's in Italian because it's supposed to be used by my mother, who doesn't speak English. So like literally my mother is a retired hairstylist, and she's helping me out shipping those devices. And so I made this for her. So this is like a website. She goes there, she can drag and drop the PDFs of the labels that are produced by DHL or whatever, and then you can print them out. So we buy those A6 labels on A4 sheets. So it's an A4 sheet with 4 A6 labels. And so with this website, you like drag and drop and can place like top left, top right, and then she can print them and ship the devices almost autonomously. So yes, like a lot of random bits, random things you develop to make your life easier. And actually, in progress right now, we are speaking with a third-party logistics service. It's still DHL. It's a different division of DHL, to basically just remove this problem from our end. So with that service, we're gonna give our stock to DHL, and they just, as orders come in, they process them. And obviously, the orders are packaged in the security envelope, so they cannot tamper with them. So it's not a trusted partner or anything. It just makes our life easier shipping the devices. So yeah, in conclusion, making hardware is fun. I think maybe it's some kind of coping mechanism, but I'm actually having fun doing this. Probably something wrong with me. And the other thing was making these slides. I kind of had to look back to the past year and a half, and I was like, well, this is pretty cool. I've done pretty much all of this as a solo engineer. So obviously there's other people helping me on the other sides of the business, so on the compliance side and all of that. But I was looking back at it, and I was like, well, this is cool. I'm proud of myself. This is probably the first time I feel like this. So I thought it needed to go in the slides. I'm really proud for me feeling proud of something, even though could have been better. Yeah. That's it. So thank you so much for coming. This is our website, our social media, also our GitHub handle if you want to see the code and stuff. And I can take questions. I think I'm a bit early. Thank you.
We can probably take one question or two in the back.
How well are you protecting against replay attacks with the pairing code over NFC?
What do you mean?
Well, you can record it. You can record NFC transactions with a flipper and then replay that.
So the communication is encrypted. We do like a noise and shake, so the communication is encrypted between the device and the phone.
Okay.
So yeah, you would have to trick me into using the flipper as the hardware wallet if you want to do that.
Okay.
Kind of thing. Yeah.
Good.
Anyone else?
Why you are using STM32 platform? It's not secure, and even like all the F models, they for our disappointment is quite vulnerable for power glitches, for multiple attacks.
So I mean, they're not secure. I think security is not kind of black and white. So there's some attacks you can do. What I was mentioning before. So the known attacks is you can extract the flash, right? You can extract the content of the flash. So if you have the seed in plain text in the flash and you can extract it, that sucks. The mitigation there is if you use the pair code. The pair code is not a pin. It's like a passphrase. It's I think we recommend 12 or 14 characters, I don't remember, alphanumeric passphrase. So if you disable the protection, you don't even need to hack it. It's just a better tool. Like you take it, you sign. There's no other protection. If you enable the protection, the flash is encrypted with a strong password. So if you manage to do those attacks that I think you're mentioning those attacks, if you manage to extract the content of the flash, it's encrypted with a pretty strong passphrase. So I think for our security model, it's fine. Yeah, obviously I wouldn't rely on it not being able to. I wouldn't rely on it to protect a secret that's not encrypted in the flash. That's for sure. But I think if you know the limitations of the device, you can use it successfully and safely anyway.
Yeah, thanks for answer. It's definitely more wider technical topic, but they can talk. It's not the only STM, but multiple other manufacturers. They are offering different features. STM, just well known. It's used in security system, in security alarm system, for example, and all hardware hackers know all the features, and even like trying to use the pair code and encrypt it is not the security. You can bypass even pin codes and lowering or overvolting the memory. It's not writing anything in the flash, and you have multiple, like millions of attacks just to perform brute forcing and decrypt it.
Yeah, I mean, I would argue that the fact that it's so well known and so well studied is probably good because we know the limitations. So we know what can be done with it. So yeah, again, I think if the alternative is buy a closed source secure element, I would rather do this and work around the limitations, knowing, like again, the assumption is the flash can be extracted. It's not that easy, but it can be extracted. So if you make those assumptions, those things are not, they don't hold. I think it's fine. Just kind of work around it with your design and your.
Yeah, unfortunately, we don't have time for another question in the hallway. Yes, but yeah, another round of applause. Thanks,
Thank
Alekos.